In this video, we're actually going to use implicit differentiation to do some of the things that we've been doing with derivatives. Hopefully, you've taken a look at some examples of just crunching through the process of finding the derivative of y with regard to x using this implicit differentiation process that we talked about. But here, we're going to actually go ahead and find slopes of tangent lines. Notice that we're going to be looking at curves in general, not specifically just functions. And similarly, we'll look at equations of tangent lines. And then we'll have a little brief discussion at the end of the video about what we're going to use this new technique with implicit differentiation for. So here we go. Let's go ahead and find the slope of the line tangent to the curve y squared minus 2xy plus x equals negative 12 at this specific x value. Cool. We'll keep that in mind. We'll log that away later on. What we normally would do here is look at this. We'd find the derivative f prime of x, and then we'd evaluate it at 4. The issue now is that we don't have some function that we're going to differentiate. So what we'll do is we'll look at y prime, and we'll look at y prime evaluated when x is equal to 4. So we'll see if we can find this using implicit differentiation, and we'll go from there. All right, so I know that if I've got y squared minus 2xy plus x equals negative 12, then what I can do is just go ahead and apply this derivative d over dx to both sides. And if you're doing this, again, I really encourage you to use the notation because we'll be able to help see a little bit about when we need to use the chain rule and when we don't. All right, so this is really time-consuming to write it all out, but I think it's really important to do. Okay, so we know we're going to have to use the chain rule here because x and y are not the same variable. We're differentiating this function with regard to a different variable, so the chain rule works this way. We're going to look at the derivative with regard to y of y squared multiplied by the derivative of y with regard to x. Over here, we've got a little product rule action because x and y are different from each other. So maybe u is 2x and v is y. That means u prime is 2 and v prime is y prime. So we're going to say minus, in parentheses, these things, 2x y prime plus 2y. The derivative of x is just 1, and the derivative of negative 12 is 0. Those last two are easy. Whew. Maybe instead of a dy over dx, I can just write y prime there. The derivative of y squared with regard to y is 2y. Then we have this y prime. I'm going to distribute my negative through here. So this is minus 2x y prime minus 2y plus 1 equals 0. You can do some algebra to find, at the very end of it all, that y prime is equal to 2y minus 1 over 2y minus 2x. That's what your derivative is. So now what we need to do is evaluate this at x equals 4. The problem is we have x's and y's in here. So as a sidebar, what we should do is find y when x equals 4. Because we need to know what that is. So what we're going to do is we're going to take x equals 4, we're going to plug it in here, and we're going to get some equation for y, and we'll see if we can solve that. So we've got y squared minus 2 times 4 times y plus 4 equals negative 12. This is a quadratic equation, so I'm going to push everything over to one side. Y squared minus 8y plus 16 equals 0, and I hopefully can factor this thing. I've got y minus 4 squared equals 0. I can see really easily now that y is going to equal 4. Okay, so now what I'm doing is I'm looking at y prime evaluated not just when x is equal to 4, but I'll say at this point, 4 comma 4, because that's the x and y value. 2 times the y4 minus 1 over 2 times the y4 minus 2 times the x4. Uh-oh, that's a problem. 7 over 0. What's going on here? Our slope is undefined. Why could that be? We should think about what possible situation we might have where our slope of tangent line doesn't exist, or the derivative doesn't exist here. There might be some important things happening when we find that. Maybe we have a vertical tangent line. Maybe we have some sort of a sharp corner. Maybe we have a point of discontinuity. We could go ahead and investigate this. So here's a picture of this curve, and I've plotted our point 4, 4. And if we go ahead and just look at this point, maybe we can see something here. Maybe it looks like there's a vertical tangent line. So we can still interpret the derivative in the same kinds of ways that we would have used to interpret the derivative. This derivative doesn't exist here because the slope of the tangent line is undefined because we have a vertical tangent line at this point. Pretty interesting stuff. Okay, so if we move on, then we can try this again and find the slope of the line tangent to this curve. Notice we've got this x value of 3. Maybe right off the bat, we could try and think like, what if we need to find the y value? Should we go ahead and do that? Let's go ahead and find this y value when x is equal to 3. Find y at x equals 3. So this is going to be 3 minus 1 squared plus y plus 2 squared equals 13. So this is 2 squared plus y plus 2 squared equals 13. I'm going to say this is really y plus 2 squared equals 13 minus 4. So that's 9. So y plus 2 is equal to plus or minus the square root of 9, or we have that y plus 2 is equal to plus or minus 3. And that's going to give us two options. One is that y is equal to 1, and the other is that y is equal to negative 5. So that's going to be kind of frustrating here. So we have two different points, 3, negative 5, and 3, 1. That means we're going to have to find two different slopes, because really we could say slopes of the lines tangent to the curve there. We could just use the plural because we have multiple lines here. We have multiple points. That should be okay because we recognize that this does not need to be a function. We can have multiple y values at the same x value. All right, let's set up the differentiation here. We're going to differentiate x minus 1 squared. We're going to differentiate with regard to x, y plus 2 squared, and we're going to differentiate with regard to x, 13. All right, we have chain rule going on here because x minus 1 is composed inside of this power function. So we'll go ahead and say that this is 2 times x minus 1 times the derivative of x minus 1, which is 1. We have chain rule here. This is going to be d over dy of y plus 2 squared times dy over dx. And then we have the derivative of 13, that's 0. So now notice this is the same kind of chain rule that we did earlier. We'll bring the 2 out front. So we have 2x minus 2 here, just by doing the distributive property. We have 2 times y plus 2 times 1 times y prime. All this to say 2x minus 2 plus 2y y prime plus 4y prime equals 0. We can solve for y prime now. 2y y prime plus 4y prime is going to equal 2 minus 2x, and that means that y prime is going to be 2 minus 2x over 2y plus 4. This is our derivative. And now we're going to go ahead and evaluate that derivative at these 2 points. All right, so let's see if I can remember all this stuff to write it down. We have 2 points, 3, negative 5, and 3, 1, and then 2 minus 2x over 2y plus 4. Let's see if I can remember that. Probably not. 3, negative 5, 3, 1, and we had that y prime was 2 minus 2x over, is it like 2y minus 4? Is that right? 2y plus 4. All right, there we go. You can do some reducing of this if you'd like. right? If I wrote it down correctly. Yep, okay. You can do some reducing of this if you'd like. You can say this is really 1 minus x over y plus 2, because there's a common factor of 2 on everything. And now what we'll do is we'll just look at y prime evaluated at 3, negative 5. That's going to be 1 minus 3 over negative 5 plus 2. So that's negative 2 over negative 3, or we could say 2/3. And we could also look at y prime evaluated at 3, 1. That's again going to be 1 minus 3, but now on the bottom we have 1 plus 2, so this is going to be negative 2/3. That should make a little bit of sense here, because what is this graph? This graph is a circle, right? We have a circle that got shifted to the right a unit and down 2 units. So our axes are like somewhere over here, right? And then our radius is the square root of 13, whatever that is, I don't know. But all of this to say, it should make sense that at this point, at x equals 3, and at this point down here when x is equal to 3, it should make sense that our tangent lines have kind of opposite slopes, right? We have this nice symmetry, but it should make sense that these are kind of flipped slopes that we have. Cool. All right, let's move on to another one. Now we're going to be finding the equation of the tangent line. The only difference now is that we'll use the slope in combination with the point that we have. So here we are guaranteed to need a y value because we need the actual point on our curve, even if our derivative doesn't have any y values in it. But we'll do the same thing. We'll find our slope, but then what we'll do is we'll use this point, we would use this point or this point in conjunction with those corresponding slopes to find a tangent line. So let's go ahead and do this. Maybe we'll grab the y value first. We're getting used to doing this, right? So we have y, not equals, minus y squared plus 1 equals 0. So maybe I'll move this all over to the right side. I've got 0 equals y squared minus y plus 2. And we have to somehow factor this thing. That's going to be annoying, right? We're not going to be able to factor this really nicely that I can see. So maybe we'll use the quadratic formula on it. And I don't really want to do that. Yeah, I think I got a typo in here. Let me put a coefficient that's going to make this thing work, because this isn't going to be nice. Let's see if we can factor this instead. That'll be good. So I'm going to go ahead and put this 3 coefficient in here. Not on that one. I'll put it right here. 3y. All right. Now we can go ahead and factor this thing, right? This is going to factor into y minus 1, y minus 2. Going to give us 2 values again. Y equals 1 and y equals 2. I'll go ahead and I'll update this on your version of the notes. I'll just get rid of this one here. And I'll call this 3y instead. All right. So what we can do now is again say we've got 2 points. 1, 1 and 1, 2. Let's go ahead and find our equation for the derivative of this thing by differentiating 3y minus the derivative of xy squared. We'll have a derivative of x squared. Look at the derivative of 1, and that'll all equal the derivative of 0. A bunch of these are pretty easy, right? But for this one, we'll need a product rule, and here, a little chain rule. You'll notice there's also a chain rule going on inside of this product rule. Whew, that's going to be kind of tricky. All right, let's do it. So the derivative of 3y with regard to x is really going to be the derivative of 3y with regard to y times the derivative of y with regard to x. Over here, we've got a product rule. So we're going to look at x and y squared. The derivative of x is 1. The derivative of y squared is going to be 2y, y prime, by using the chain rule here. And then we've got 2x, 0, and 0. So let's go ahead and write all this out. We have a 3y prime minus 2xy prime plus y squared plus 2x equals 0. Let's distribute this negative, solve for y prime, and then we can move on. 3y prime minus 2x y prime, I almost missed a y there, minus y squared plus 2x equals 0. And so we end up with 3y prime minus 2xy prime equals 2x minus y squared. And we should be able to get that y prime is equal to 2x minus y squared all over 3y minus 2xy. There's our derivative. Here are our 2 points. So now we'll move forward, and instead of just finding the slopes at these 2 points, we'll actually combine this all together to get a tangent line at each of these 2 points. I'm going to have to do this piece by piece because I'm never going to remember all this. So y prime equals 2x minus y squared. Let's see if I can write this up here. 2x minus y squared over 3y minus 2xy, I think that was. Yep, and then 1, 1, and 1, 2. Those points are easy. And maybe I'll go ahead and say y prime evaluated at 1, 1 is going to be 2 times 1 minus 1 squared over 3 times 1 minus 2 times 1 times 1. So this is 2 minus 1 over 3 minus 2. That's a slope of 1. But now we don't have to stop there. We can go ahead and say y is equal to a slope of 1, an x value of 1, and a y value of 1. So this is x minus 1 plus 1, or y equals x. Maybe I'll write this down here. That is our equation of our tangent line at this red point. For the blue one, then, we'll say y prime is 1, or evaluated at 1, 2. That's going to be 2 times 1 minus 2 squared over 3 times 2 minus 2 times 1 times 2. So this is 2 minus 4, that's negative 2, over 6 minus 4, that's 2. That's a slope of negative 1. So now we can use our equation of our line to get negative x plus 1 plus 2, or so this negative 1 times negative 1 is a positive 1 here, plus 2. So we have y equals negative x plus 3. And there's our equation of our second tangent line. Okay, so we can do a whole bunch of things. We can think more carefully about finding horizontal tangent lines. We can still say, oh, okay, slopes are going to be 0 on those. So we need to set y prime equal to 0. So that might be something that we could still do. We can find vertical tangent lines like we did in that first example. Were there places where the tangent line wouldn't exist? Or are we saying, can we find the slope of the tangent line at any point? Well, each of these curves are still going to have like a domain, right? So if we're looking at a point over here, an x value over here and a y value over here, it's not actually on our curve, right? So we still have this idea of like, we need to be looking at points on the curve specifically, and sometimes that's not as clear as what we would like it to be for some of these kinds of examples. We can't just pick an arbitrary x value and plug it into our derivative rule. We need to be finding coordinate points that are actually on our curve. We have to be doing that with our regular functions, but it just seems a little bit more natural to do there, and it's a little bit more unnatural to do here. I find that students in general, they're not as used to working with these kinds of non-function curves, and so that part can get a little lost. So just be careful about that. What are we going to do now? What are we off to next? Well, we can use this idea of implicit differentiation to do a bunch of stuff. In the next video, we're going to look at related rates. This is just applying implicit differentiation to some word problems, but we're going to notice that we don't have to be using x's and y's, right? If we had something like a squared plus b squared equals 0, we could differentiate all of this stuff with regard to a. Oops, let me write this a little bit more carefully. 0. And we know we need to use the chain rule. But we could also differentiate this with regard to t or some other variable. And now all that means is that, hey, we use the chain rule on both of those pieces. Use the chain rule anytime you need to. Anytime that variable of differentiation is not the same variable as what you have in the term. No problems. Then what we'll do is we'll finish out a bunch of other function derivatives. We're going to use implicit differentiation to help find derivatives of logarithm functions and inverse trig functions, and we'll use general exponential functions too. And that's just going to be by using this nice property of inverses and then using implicit differentiation on these new equations here. So that's going to be pretty fun. And then once we unlock the secret of the derivative of logs, we're going to be able to use logarithmic differentiation, which is just going to apply logarithms to equations and then use implicit differentiation because logs are really nice. Contrary to what you might believe, logs are wonderful to work with. So we're going to use all of the nice properties of logarithms to help us out here when we use logarithmic differentiation. That's what we've got, and that's the last little bit of this section of videos before we move on to actual applications of these derivatives.